Hello friends, welcome back to our series of lectures on structure of atom. In today's session I am going to talk to you about Bohr's model and Sommerfeld's modifications of Bohr's model there. Now before we come to Bohr's model, let's try to recall what we've done so far. Basically you will recall that in the first session we talked about the very concept of the origin of concept of atom from philosophical times. And then we came down to Dalton's atomic theory, followed by Thomson's experiments and all, Thomson's model, and then Geiger's experiment, and ultimately we came down to Rutherford's model, which basically is that there is a nucleus in the center and the electron is revolving around that. So that's where we ended there, and also we showed there that this model of atom, that's what proposed by Rutherford, was not a good enough model, because according to this model, atoms should not be stable, because the electron which is revolving around the nucleus will radiate and eventually fall into the nucleus. So that's where we stopped the first session. In the second session, we talked about a different kind of domain altogether. We talked about the classical mechanics and did kind of lay out the successes and the failures of classical mechanics. And in the context of failure, or you say inadequacies of classical mechanics, we highlighted three main experiments. One was black body radiation, second was photoelectric effect, and third was the line spectrum from atoms. Now then we came down to the concept of quantization, that is discreteness, that is the concept of quantization as proposed by Max Planck in 1900. So basically quantization basically means is discreteness. There is no continuity of things, that things are discrete, whether it's energy or other things over there. We'll come down to that very often when we talk about structure of atom there. Then we used it in explaining the results of black body radiation and also the photoelectric effect. In case of black body radiation, we talked about quantization of energy, whereas in case of photoelectric effect, we extended, it was extended by Einstein to radiation. Okay, and then we left at the next challenge, that is the atomic line spectrum. We showed that atoms, that hot atoms give spectra which are line spectra. And Rutherford's model, that is the model which was available at that point of time, was not able to explain, because according to that model, when the electron is radiating out, when it's going to spiral into the nucleus, it will give all possible radiations there and not discrete lines over there. That there again, the then available model of atom, that is Rutherford's model, was not good enough to explain the atomic line spectrum. And that's where we had to now bring in Bohr's model there. So Rutherford's model was 1911, then Bohr's model came about 2 years later, that is in 1913. Now it is very interesting to note that Niels Bohr proposed a model of atom, and this model of atom was basically a mix of a lot of classical and quantum mechanical ideas there. Because basically, as I perceive it, Bohr actually used a lot of concepts available at that point of time, put them together, gave some new ideas, and put together a model which we now know fairly well as Bohr's model, which was fairly good to an extent. We'll discuss about all that. So basically what he did, he used first, that is a Planck's concept of quantization. Because prior to that, that is still about 1911, that's Rutherford's model, there was no quantization used over there. So for the first time, quantization was used in the context of atom was by Bohr there. So that's one thing he used. Secondly, he used Einstein's concept of photons, that is a photon is emitted or absorbed. We'll come to that as well. And third he used was Rutherford's idea of nucleus. Because if you remember that I highlighted in the very first session, that is the biggest contribution of Rutherford was that he gave the concept of nucleus, which till today we know that atom has a nucleus and it is in the center of the atom over there. So that's a very big contribution from Rutherford there. Excuse me for that. Okay, now in addition to that, he added a few new concepts. So that is how the model was built up there. He used a few known things there and he gave in a few new things from his own side there. Now let's understand what is this model of atom as proposed by Bohr there. So the first thing basically picked up from Rutherford's idea, that is there is a nucleus and electron is moving around nucleus in circular paths called as orbits. So that's basically he borrowed from Rutherford there. And also it made a statement over there, that is because when it is undergoing a circular motion, so they know that there are two kind of forces there. One, electron is an electrically charged particle, nucleus is positive, so there will be electrostatic attraction over there. That means nucleus will try to pull electron toward itself. And secondly, since the electron is moving in circular motion, it will have some kind of an acceleration due to circular motion over there. That is some kind of centrifugal force over there. So these two forces are matching. The two forces are equal. That's how it stays in the circle over there. If they are not equal, it will either come down or it will fly off. Okay. So that is the first proposition. That is the starting point for Bohr's model over there. Thereafter, that's very important here. He used the concept of quantization to suggest that only certain electron orbits are allowed there. That means that's where the concept of quantization comes in there. Because when Rutherford model was there was no restriction of where the electron will be. It is just moving around the nucleus, but where it is, we do not know. But Bohr tried to establish that by saying that only certain orbits around the nucleus are allowed over there, and they are given by a certain amount of energy, En, and then this n is a quantifier there as a quantum number there. And the expression for En was En is equal to minus of Rh, that's Rydberg's constant over there, 1 by n square, when n can vary from 1 to 3 and so on and so forth up to infinity. Now, and then the shells there, that means this is n is equal to 1 shell, 2, 3, 4. So they were given names as K shell, L shell, M shell, N shell. So we still use it sometimes, but not necessarily. Primarily, our understanding is that we're talking about energy, the orbits over there, which are basically energy levels, and these energy levels are characterized in terms of the principal quantum number called as n. Okay, that is one bit. So that means basically, so we have a nucleus and we have an electron moving around the nucleus in an orbit. That's one bit, and only certain orbits are allowed for which energy is given by the following formulation there. That means it cannot be any orbit around the nucleus where the electron can be there. It can be there only in certain orbits wherein the energy happens to be given by this particular expression there. So that is the concept of quantization there. That's one bit. Going further, now if you look at the energy expression, if you try to plot that energy, what you find is that we have a nucleus in the center. Now suppose we think of the electron to be at infinity from the nucleus, very, very far from the nucleus. In that case, there is no force of attraction between the nucleus and the electron. So that state is arbitrarily given. That means when n is equal to infinity, as we given energy to equal to 0. That means the energy of a free electron is basically, it is outside the influence of the nucleus, that is arbitrarily given a value of 0. And then what happens is, in an energy expression we have a negative sign there, minus of Rh. Okay, so that minus indicates that is as the electron comes closer and closer to the nucleus, some kind of a attraction comes into play. As a consequence, the energy decreases. Some kind of a stabilization is coming over there. So that's what you find here. That means, so the energy, say for n is equal to 4 level is Rh by 16 minus Rh by 9 minus Rh by 4 and so on and so forth. It goes on decreasing. And for n is equal to 1, it happens to be minus Rh. That's the minimum energy we have over there. Okay. Now going further to this level there, for n is equal to 1 is called as a ground state. That is typical in all kind of spectroscopies which we will be talking about at a later stage. That is n is equal to 1, that is a ground state. The first level in any quantized energy level systems is called as a ground state there. So it's true over here. Now what you find from here is that with increase in the value of n, the energy becomes lesser and lesser negative. That's very important to understand. What we find is that here for n is equal to 1, energy is minus Rh. When it becomes n is equal to 2, it becomes minus Rh by 4. It is 1/4 of that. That means it is lesser negative. Going further, for n is equal to 3, it becomes minus Rh by 9. It is still less, so on and so forth. That means as n increases, the energy becomes lesser and lesser negative, which actually means is it becomes more and more positive. So what it means is that is as n increases, the energy increases. So there is a direct relationship between n and the energy of the orbit over there. So it is a relative thing over there. Okay. Now let's go further and see the next proposition. That means one was what we have seen so far is that is there's a nucleus, electron is moving around the nucleus. only certain orbits are allowed which has got energy is given by minus En is equal to minus RH and so on and so forth. And then we have seen what are the energy levels there, and then we also know that for electron to be at infinity from the nucleus, energy is given as a value of 0. As electron comes closer and closer to the nucleus, energy decreases. That's where we are. The next proposition which came from Bohr was, that is the second thing, very, very important there, which was a new proposal there. He suggested, he rather proposed it, that is the electron's orbital angular momentum around the nucleus is quantized. What does it mean? That means because we know that electron is executing circular motion around the nucleus. So since it's an angular kind of a motion, it has an angular momentum over there. So he proposed that angular momentum is quantized, and is the following expression given for that. That is mve, that is mass of electron, v is the velocity of electron, r is the radius of the orbit in which it is moving, is given by nh by 2 pi, and again is the principal quantum number having values of 1, 2, 3 and so on and so forth. H is Planck's constant, and h by 2 pi actually is called as action constant, or sometimes use it as h cross. Now, what you find is that this proposition was a new proposition there, and very important thing we have to note here is that is Bohr has used the same quantum number n to quantize the energy, because the previous expression we had was En is equal to so and so forth. That means energy in terms of the quantum number n. Now we are talking about even the momentum quantized in terms of quantum number. That means the same quantum number n is used to quantize the energy as well as the angular momentum there. And this expression could be then used to work out the size of the orbits. That means what will be the size of the orbit, how far, what will be the radius of the orbit where the electron will be able to exist over there. Okay, so that is only certain orbits will be allowed for which this following expression holds true. That means where mvr is equal to nh by 2 pi. And so from this expression we can work out an expression for Rn, that is Rn happens to be the radius of nth orbit. That will be given by following expression, n square h square by 4 pi square me e4, where n again varies from 1, 2, 3, 4 and so on and so forth. So what you find is in this expression you find that h is a constant, that's a Planck's constant, pi you know is a constant, mass of electron is a constant, and charge of electron also is a constant. So you find is other than n square, everything else is a constant. So we can write it as that Rn to be equal to n square, which is the variable here, into a naught. And this a naught is given by the following expression, is h square by 4 pi square me e4, and this actually is called as Bohr's radius. That means when n is equal to 1, so this will become Rm1 will be equal to a naught. So that means a naught actually defines the radius of the very first orbit closest to the nucleus, the so-called ground state over there. Okay, now it's important to note here that Rn varies as square of the principal quantum number. What does it mean? Let's have a look at this picture here. So suppose this is our nucleus here, and the smaller circle over here is having a radius a naught, that's the Bohr's radius. So this is n is equal to 1 level. N is equal to 2 level will be 4 times a naught, so that will be much larger this thing. N is equal to 3 will be 9 times a naught, and n is equal to 4 will be equal to 16 times a naught. That means as n increases, the orbit becomes larger and larger, much, it's not that linear. It doesn't become 2 times, 3 times, 4 times, it becomes 4 times, 9 times, 16 times, 25 times and so on and so forth. Okay, so that's very, very important to understand that Rn varies as square of the principal quantum number, that is n. Okay, let's go further and see that another new proposition which is very, very crucial from Bohr's model point of view, that because basically you remember that when we talked about Rutherford's model, there was a big question on Rutherford's model, was that when electron, a charged particle, is moving around another charged particle, that is a nucleus, it must radiate, which is what is expected from electromagnetism. But here Bohr proposed a very new bold idea over there. He said the energy of electron does not change as long as it stays in a given orbit there. So this was contrary to the then known beliefs, that is the classical mechanics from electromagnetism. Electron must radiate and give out energy and come down to the nucleus. But that's where a new proposition came. The crux of Bohr's model was that the energy of electron in the given orbit does not change as long as the electron is in that particular orbit over there. So in that sense, they are called as stationary states. That means in that particular orbit, the energy of electron does not change. It was a new proposition, a very, very important proposition over there. Okay, then next thing we talked about was that that's where Einstein's idea of photon comes into play. He said, okay, so we have a nucleus, and these are different energy levels over there, K, L, M, N, and so on and so forth shells. Or you can say N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4, N is equal to 5 orbits over there. Okay. Now, so suppose you have an electron somewhere here, say N is equal to 2 level over there. And if I give some kind of a energy, electromagnetic radiation, a photon comes in there that strikes the electron, and the electron goes to higher energy level. It absorbs. So as long as electron is here in this particular orbit, energy will not be changing. But if I give energy from outside and there is an orbit change, so then that means when the energy of the electron becomes more, it goes to higher energy level with that particular energy there, which is sum of the earlier energy and the energy given by the photon over there. So that is called as excitation. This process is by absorption of photon, and the process is called as excitation because electron goes from a lower energy level to higher energy level. And second possibility is, suppose the electron is at higher energy level, it can come down to lower energy level, and this difference in energy, say E5 minus E2, that will be coming out as a photon over there. So this is called as relaxation or emission process there. Okay, so that is again basically it's an extension of the idea of Einstein with what he proposed in the context of photoelectric effect. You remember that in the photoelectric effect, Einstein used this quantization of radiation in terms of, that means the radiation is considered as a stream of photons. That's a particle nature of radiation. Okay, let's go further and see that this particular idea can then very well be used because when the electron is in a lower energy level, can take up a photon, go to higher energy level, and from higher energy level it can come down to lower energy level and give out photons there. And that is what exactly happens when we talk about the atomic line spectrum there. And you remember, you must have learned about this in your school also, that in the hydrogen atom spectrum, you get variety of lines over there, Lyman series, Bohrs series, Paschen series, and so on and so forth. These series are nothing but set of lines over there. So that is typically the line spectrum. And what you find from here is, and this particular expression, this diagram shows here, that is, these are the different energy levels. This is N is equal to infinity level, energy is 0. It is given in electron volt terms there. And there are different energy levels there. And what you find is, when the electron from higher energy level can come down to lower energy levels, so this particular set of lines will be following in the Paschen series over there. So that means what it amounts to saying is, that is, Bohr's model was successful in explaining the origin of line spectrum of hydrogen atom. Basically what happened was, so the energy levels what was proposed by Bohr, if you use those energy levels and try to find out the differences in different energies of the two levels, say from a higher level to lower level when it's coming, so that happens to be exactly matching with what was experimentally observed in these different lines of in the spectrum, Lyman series and so on and so forth. And that means we said that there is a one-to-one correspondence between what is experimentally observed and what is theoretically predicted by Bohr's model in terms of the spectrum for hydrogen atom. I am re-emphasizing it is only in the context of hydrogen atom. That is one bit. However, what was found is that if we use a sophisticated instrument, that means when we talk about high resolution instrument there, we find that these lines which are observed here, that was matching earlier, but what we find is that these lines, there was some kind of a fine structure coming there. That means maybe each line may be split into 2 or 3 lines and so on and so forth. So this fine structure, where is the origin of that one, that was not explained by Bohr over there. That means as long as a low resolution spectrum comes, a low resolution atomic line spectrum experimentally observed, and what is predicted by Bohr's model, the two are perfectly in agreement over there. So to that extent, Bohr's model was very successful there. But when we try to use that model to explain the observations in high resolution spectrum, we found that there was it was inadequate there because there was a lot of fine structure coming over there. Each line was split into 2 or 3 lines. That was not explained on the basis of Bohr's model. So Bohr's model was inadequate to explain. It could not explain the fine structure in atomic line spectrum at high resolution there. That is one inadequacy there. Going further, it also doesn't explain the spectra for systems having more than one atom there, one electron. That is what exactly I said here. I said that Bohr's model was good enough to explain the spectrum for hydrogen atom. Hydrogen atom is the one which has got only one electron. That means there is one nucleus and one electron. The system is good enough. You are able to explain the spectrum there. Similarly, if I take, say, helium ion, you know that helium has got a nuclear charge of 2 units and there are 2 electrons in that. And if I knock off one electron, I get helium ion. So that again is a system similar to hydrogen atom. Because there is one nucleus, there are only 2 particles there, one nucleus and one electron. Even for helium atom, helium ion, the spectrum experimentally observed and theoretically predicted by Bohr's model were matching. But when it comes to helium atom per se, helium ion was fine. Helium ion could be explained, but helium atom spectrum where there were 2 electrons, or lithium atom or any other atom for that matter, when there is more than one electron, the spectrum could not be explained because there were more lines coming over there, so that could not be explained on the basis of Bohr's model. So you find that Bohr's model was actually much better than the earlier model, that is Rutherford's model, was able to successfully explain the stability, because we said the energy, that means when the electron is in a given orbit, it will not radiate. So it is stable in that sense of it. And secondly, it also explained the hydrogen atom spectrum there. So to that extent, it was successful, but it could not explain the high resolution spectrum and also the spectrum for atoms having more than one electron there. Going further, this problem of fine structure in high resolution spectrum was addressed by Sommerfeld. Sommerfeld basically worked on Bohr's model and modified it. And in that sense, it was sometimes we call it as Sommerfeld's model there. Let's understand what are the 2 modifications given by Sommerfeld there. Sommerfeld said, contrary to what Bohr proposed there is a nucleus in the center and the electron is moving around in different orbits which are circular in nature. Okay, and then we talked about that the balancing of attractive influence of nucleus and electron with the centrifugal force of the that's angular motion of the electron in the orbit over there. Sommerfeld suggested the 2 modifications he proposed. The first one was that the electron doesn't move around the nucleus only in circular orbits, rather he proposed that it moves around the nucleus in elliptical orbits there, with the nucleus at one of the focus over there. You know that in an ellipse, suppose you look at this blue ellipse over there. So we know that for any ellipse there are 2 foci, what you want to call it as. One will be somewhere here, one will be somewhere here there. And what he proposed was that is the nucleus is at one of the focus of the ellipse there, and then the electron moves around it different elliptical orbits there. And what you're seeing is that I'm shown there are 3 orbits in this case. 2 of these happen to be elliptical and 1 happens to be circular there. That is what exactly was proposed by Sommerfeld. Sommerfeld said that electron moves around the nucleus in elliptical orbits, and in an elliptical orbit, if the minor axis and major axis happen to be equal, that becomes a circle. So circle is a special case of an ellipse over there. To that extent, so this when there is a continuity there, Bohr's model becomes a special case of Sommerfeld's proposition that electron moves in elliptical orbits over there. Okay, so as I just said, the Bohr's circular orbits are a special case of elliptical orbits over there when the minor axis and major axis happen to be equal there. And then Sommerfeld used 2 quantum numbers, K and NR, and they are called as azimuthal quantum number and radial quantum numbers over there. So it was extension from what Bohr said. Bohr was proposing only one particular quantum number, that is n, to quantize the energy as well as the angular momentum over there. But Sommerfeld proposed new quantum number K and NR, and also n is continued over there. Let's see it there. So the 2 quantum numbers K and NR, they are required. I tell you why did we need 2 quantum numbers over there, and also there is a relationship between the principal quantum number and then these 2 new quantum numbers K and NR over there. Let's understand why do we need these two things there. The reason for that is that when, suppose this is my nucleus over there, of the nucleus of the atom there, and electron is moving around in this elliptical orbit over there. Now what you find that as the electron moves around the nucleus, we find that, suppose this is the position of electron at point 1, at time 1, it goes further, it comes somewhere here, then it comes here. What you find is, as the electron is moving in elliptical orbit around the nucleus, which is stationary, so you find that the distance of electron is changing continuously over there. It increases, comes to a maximum there, then starts decreasing, comes to a minimum there, and then starts increasing again. Okay, so that means there is a distance of the electron from the nucleus is not constant as was proposed by Bohr. When we talked about circular orbit, then electron has the same distance every time, anywhere it is on the in the orbit, it has the same distance there. But in case of ellipse, the distance changes. That is one. Secondly, that when the electron is moving like this, we find that even the angle is also variable there. So suppose electron is here, so it is with this major axis, it's making angle phi over there. When it becomes here, the phi is changing, it's here changing, and so on and so forth. That doesn't happen in case of the Bohr's proposition there. So since in case of elliptical motion around the nucleus, we needed two new quantum numbers, that is, it was proposed by Sommerfeld, that is K and Nr, and then this K and Nr, the Nr is called as the radial quantum number, and K is the azimuthal. Azimuthal basically refers to the motion, circular motion kind of a thing, angular motion, not circular, angular motion there. Now, and then we find that N, that's the principal quantum number, and K and Nr are related by following this thing, following relationship, and K varies from 1 to N. When K is equal to 1, Nr will be equal to 0, and so on and so forth. And what you find from here is that, say, if you remember, we have for Bohr's model, we had variable of N as N is equal to 1, 2, 3, 4, up to infinity it can go. Now suppose I take a situation, say for N is equal to 3. When N is equal to 3, there are 3 possible orbits over there. 2 of them will be elliptical and 1 is circular. Let's understand this one. Now, so this orbit here, the blue line over here, this is when N is equal to 3, but K happens to be 1. Because I just said, if you remember in the previous slide, we said that K can vary from 1 to N. So, and N happens to be 3, so the K can vary from 1 to 3. Okay. So when K is equal to 1, we have got the following elliptical orbit over there. When K is equal to 2, this becomes this orbit over there. When K is equal to 3, this becomes this, which is same as the N is equal to 3 level there. So what you find that what actually it meant was the following, that is N is equal to 3 shell, that is N is equal to 3 orbit, so to say, in case of Bohr's model, now becomes N is equal to 3 shell, and it has got 3 subshells over there. Means all these 3 orbits I am showing here, K is equal to 1, K is equal to 2, and K is equal to 3 level, all the 3 are having the same value of N. That means, and also we find that they have got the same energy. Okay, but they are basically K is equal to 1 shell is called as 3s subshell, because N happens to be 3, so it will be 3s subshell. K is equal to 2 was 3p subshell, K is equal to 3 was 3d subshell there. So there are 3 sub-levels of N is equal to 3 level. But since, as I just mentioned before, however, these 3 orbits, the so-called 3 subshells, have same energy in case of hydrogen atom, so it could not explain the fine structure. Because basically, fine structure basically means what? When a line is coming because the 2 energy levels involved in the transition. Say in Bohr's model, say there is a transition from N is equal to 4 level to N is equal to 2 level. Okay, so what will be the energy of that? Where will be the location of the line will be? That will depend on the energy equal to 4th level, energy minus energy of the 2nd level. So that will be the delta E, which will be observed in the line spectrum there. Now, if the same line is in high resolution spectrum is found to be having more than one line over there, so that means there have to be more than one energy levels there. That means each level, say N is equal to 2 level or N is equal to 4 level, there should be some kind of a splitting of the energy levels there. So that is not what was proposed by Sommerfeld by proposing elliptical orbits there. So what you find is since the three subshells have got the same energy, so it was a step ahead of what Bohr proposed, but it still could not explain the fine structure as was observed experimentally under high resolution spectrum there. Second modification was that Sommerfeld said, since electron is moving in elliptical path, it will, that means that suppose this is a nucleus here and electron is moving in this elliptical path. As it is moving, it will have different velocities. What does it mean is the following. Suppose nucleus is there, electron is somewhere here, it has certain velocity there. As it goes farther and farther from the nucleus, it becomes slower and slower. And as it comes closer and closer, it becomes fastest and farther and faster and faster. When it comes closest to this one, that becomes the fastest one. That means the speed of electron is minimum when it is farthest from the nucleus and is maximum when it is closest from the nucleus. That is what we have is, that is the speed of electron or the velocity of electron as it is moving around the nucleus in an elliptical orbit, it is changing. It is changing, it is continuously varying there. And since the speed of electron is fairly large as it is moving under influence of a nucleus, we find that there could be relativistic changes in the mass of electron. That means, because all this discussion we have had so far is, that is, we talked about electron to have a mass of me. That is called as a rest mass of the electron. That means when the electron is at rest, because that mass is not variable there. But when the electron is moving at high velocities, the mass of electron actually changes. And what it means in this present context is, that is, when the electron is somewhere here, it has got a certain mass. When it comes closer, the mass changes over there. So when the mass changes, then what happens as a consequence of it? Let's understand this. So the first consequence of this, that is the relativistic consideration of mass of electron, is that is the energy expression now changes. Because in Bohr's model, we had En to be equal to minus of RH and so on and so forth. That means it was dependent only on the quantum number n. But now that it is found, I'm not giving the expressions over there because that is not in your course. What is found is, that is, the energy now changes on both n and k. What does it mean? What does it mean is, that is, you just saw in Sommerfeld's case, say when n is equal to 3 level, n is equal to 3 shell, there was 3 subshells. And we said that they have got the same energy. But now, because of this relativistic motion, we find that these 3 levels, the energy is not the same. And n is equal to 3, k is equal to 1 has got one energy, n is equal to 3, k is equal to 2 has another energy, and so on and so forth. As a consequence, let's understand, look at the energy level diagram here. So let's look at a transition from n is equal to 3 level to n is equal to 2 level. So in case of Bohr's model, n is equal to 3 has certain amount of energy, which is equal to E3. N is equal to 2 has energy equal to E2. So this line will be observed as at energy equal to E3 minus E2. Now there will be only one line coming over there. But now in the light of what we just discussed about the relativistic mass of electron and the energy of electron in different subshells changing, what do we find now according to Sommerfeld's modification is the following. Now, so this n is equal to 3 level we just discussed. Let's understand that first one. When n is equal to 3 level, you can have, we just showed that there are 3 possibilities of k shells over there. This is k is equal to 1, k is equal to 2, k is equal to 3. So there are 3 subshells possible over there. Okay. And what you find is that the energies of k is equal to 1, k is equal to 2, k is equal to 3 are different. Okay. Similarly, for n is equal to 2, there will be 2 values of k possible there, k is equal to 1 and k is equal to 2. That means, and the 2 have got same, not the same energy, slightly different energies over there. Okay. So what you find is, in case of Bohr model, there was only one orbit, n is equal to 3 level, only one orbit, n is equal to 2 level. But now, for n is equal to 3 level, 3 shell, there are 3 subshells in case of Sommerfeld. For n is equal to 2 level, there are 2 subshells over there. And now, when there is a transition from n is equal to 3 to n is equal to 2, there are 3 possibilities. You can have a transition from K3 to K2 level like this, or this or this. So there are three transitions coming there. So since these three transitions will have different energies there, this energy is same as this one, so that line will be coming. But this energy will be slightly different from this one, so line will be slightly different there. And this will be slightly more energy there, it will come at a different position over there. So that means this n is equal to 3 to 2 line, which was coming as a single line in case of Bohr's model, will now come as 3 lines over there. So that explains the fine structure, what was experimentally observed in case of high resolution spectrum over there. Okay, let's go ahead and try to now find one more very important observation here. That is, now we just said that as the electron is moving around the nucleus in an elliptical orbit there, the mass is changing, and because of relativistic considerations there, then what happens now? What happens is, as the electron comes closer to the nucleus, its velocity increases and the mass will change. And as a consequence, what happens is, the balance between the nucleus and the electron gets slightly distorted. And as a consequence, electron doesn't continue to be moving in the same elliptic orbit. There's some kind of a disturbance comes. That means it deviates from the elliptical path there. And this is the kind of motion electron executes there. And this is called as the actual orbit of electron around the nucleus is a rosette shape. It is not ellipse particularly. Because of this elliptical orbit, when the mass of electron is changing, when it comes close to a nucleus, this ellipse gets slightly distorted. Every time it reaches close to the nucleus, ellipse slightly distorts, becomes a new ellipse, and this continues there, and that is the kind of motion what we are expecting in case of electron moving in elliptical orbit, and its mass changing because of the relativistic considerations there. Okay, I think let's sum up where we are right now. So basically, I would like to sum it up in terms of the limitations of Bohr's model. So we have seen that we have moved far ahead of what was proposed by Rutherford earlier. Bohr's model, we have seen that is there is a nucleus there, and there is an electron moving in an orbit over there, and we talked about stationary states. Energy of electron doesn't change when it is in a given orbit there. And then we also said the electron can change the orbit. In that process, energy change can take place. It can absorb energy or it can emit energy. And then we found that this model of Bohr was able to explain the hydrogen atom spectrum, but was not good enough to explain the spectrum, the fine structure in spectrum of hydrogen atom under high resolution spectrum. And also it could not explain the spectra for multi-electron atoms there. Okay, now let's try to kind of outline the limitations there. So that's just I mentioned over there, could not explain the fine structure line in the high resolution spectroscopy. And then also, in addition to what we discussed so far, it could not account for Siemens effect. There was a further observations on that. That is, the spectral lines, if I take a spectrum, say atomic spectrum, normally you get certain lines there, but if you put the system into a magnetic field, we find there are more lines coming there. So their origin could not be explained by Bohr's model. Similarly, under electrical field also there were more lines. That's called a Stark's effect. That also could not be explained. And also, very importantly, though Bohr's model was good enough in that sense that it would explain the spectrum of hydrogen atom, but it could not give no justification why stationary states. It was a good proposition, but why does not the electron radiate energy when it is in a given orbit there? Because this is contrary to what was expected from classical mechanics there. So there was no justification for that. He said it will be like this, that's all. It's a proposition, but there's no justification for that proposition. And also similarly, he could not justify why should the angular momentum of electron be quantized over there. Okay, I think that's where we wind up for today. And in the next session, we will take up de Broglie's idea of matter waves and Heisenberg's uncertainty principle, because these are the two things which we need to understand before we move to the next model, which is the current understanding of the spectrum of the structure of atom, that is the quantum mechanical model. Because we started with the Rutherford's model, we moved on to Bohr's model and the Sommerfeld's modification of Bohr's model. To some extent, things are better off now. But we need to continue with what we talked earlier about the concept of quantization, because the current understanding of structure of atom is in terms of quantum mechanical model. So that is our ultimate target over there. So we would like to build up for that, and for that we need to understand first the de Broglie's matter waves and Heisenberg's uncertainty principle and their significance. It will be a short session over there. So then we will see that how do we move ahead and talk about the quantum mechanical model. Thank you very much.